耶，每天都要来读书，逼迫自己读书。像应该也有很多人是呃，无人甲你逼，你就不会去读册。好啦，不要紧，咱即马就来读册吼。顶届呢，阮读阮是到74啊，好，即个咱为Brandon Fields 开始，好，sorry，哦，前也不用前情提要了，反正好，还是讲一下，就是我们今天呢，也还是读这个 Turbulent Flows 这个 by Stephen 好，那接下来的书单呢，就是我会这个在这个档案上面有写哈，就是The Elegant Universe。那这本书呢，我想我应该很快拿到了，应该是明天或后天就会拿到，到时候我们就会直接插播去那本书去。那也是很就是如果大家有在看的话，就是希望你可以投递你的书单，只要我找得到这本书，就可以想办法，拿到这本书之后呢，就是跟大家在线上一起读这本书。我们来解决，没有解决啊，不是解决，解决我自己。你解决一个就是，怎么就是想看的书其实很多，我们大家也想培养这个阅读的习惯，但是不是这么的容易哈，就是对，希望你就是在看到我的直播的时候，看到我这么努力读书，我们就一起努力读书这样。OK 哈，OK，好了，所以这是线上阅览室啦。这个所谓的阅览室呢，之所以会取名叫阅览室，大概就是我高中的时候努力读书的时候的地方，被称作为阅览室啦。努力读什么书不一定，我不知道是什么书。教科书啊，教科书。OK，好，话不多说哈，我们现在就开始，因为我们现在我可能每一集都可以就是稍微提一下，就是我们大概会看书个1个小时，然后1个小时之后呢，就会简单的就是做结一下我看到的什么内容，然后跟大家分享。当然，这些内容呢，是我读完这本书的那个部分转化出来的东西，是我自己咀嚼后出的成果，而且是现场咀嚼，所以就没有那么的精细。对，但是如果大家有兴趣的话，就是想要在 review 里面的内容，我们可以随时回来看看，就是要怎么让自己可以更深入的去看这本书的内容，然后我们可以一起去了解一下他想讲的是什么东西，你可以从这本书里面学到什么东西之类的。哎，有人分享这些蛮有趣的事情，其实很像线上读书会，但是像又不像。目前突然想不出来该怎么说，就是不真不不这么真的是读书会的感觉，可能比读书会的压力还要小一点，因为只有我在读，没有啦，开玩笑。好，差不多时间开始。 Okay, yeah. So I think this is the end of the reading for this time's streaming. Yeah. So what I did is from reading from page 74 to page 86. It's actually 85. Yeah. So briefly, I would like to briefly state what did I read? What did I read? In the previous time. Yeah. So, the first section is called 3.7 is called random views, and then we go to the 3.8 probability and averaging, and then we jump into chapter 4, which is called mean flow equation. So we come back to the physics part, and try to apply all these quantities like the means and the probability density function and correlation, whatever this kind of things into the Navier-Stokes equation. But before we get into this, I still like to I'll try to describe what is a random fields I just read. So basically, last time we got a concept about a concept about a correlation, right? A random process. And a random process is like they give you a time series event and try to see that is the the probability at each time, and we combine the probability at one. I would say that is 1 point 1 time. So you have a fixed position point and a fixed time, and you got a one time CDF or BDF, whatever. Yes, but we located only for one position, right? So if we want to extend to the whole flows, like in the velocity fields, you want to see the whole fields view. You probably need to not just for the time the time scales, not the scales, but not just look into a time series, but also the whole the region that you want to uh, investigate, right? So random fields is just like you try to you try to join all the one time and the 1 point CDF or PDF of the velocity together. Mhm. So uh, after you do so, you probably try to find the mean velocity fields. To take the mean velocity fields. I would say because I have I think I have the equation on my book, but I cannot read it out for you. Probably I can. So there's okay. It is a three-dimensional mean velocity fields. The joint probabilities is like the mean velocity equals to triple integral is from the minus negative infinity to the infinity. So you will have your your sample space times your probability function. So you has a sample and times your probability, and this triple integral is from we have one direction, two direction, and three direction, right? So we take the integral in one and two and the three directions space sample space, and then we will get the mean velocity by this operation. Yeah. But so as you can see, like if we get a mean velocity, right? But at a certain point and at a certain time, like a small u that we what we just discussed, that the mean velocity we use like a capital U, and the angle brackets to denote that is the mean velocity field. But for the true velocity field, that is containing the mean velocity and the fluctuating velocity. So this fluctuating velocity is just like at that point you have a mean, right? And plus your fluctuating will become your the actual velocity, random one. I will say random one because we are still stay in the random field. So that is a separation from your mean flow and the fluctuating flow. So this is a very important concept that when we jump into the chapter 4, we will use this kind of concept. Actually, this this concept is derived by from 1894 by Reynolds. Wow, that's very classic one. So, but that still stayed in the probabilities field. So like you go got this 1 time covariance of the velocity that you got ui lowercase ui and lowercase uj, and get the correlation. It's somehow in the next chapter we'll directly call Reynolds traces. Yeah. So we'll come back to Reynolds trace. And so that is the way to describe your flow, your turbulence flow in the probabilities method. But you probably cannot say a random velocity field can fully categorize by your probability, because you cannot get all the data, or just not to say data. You cannot go get all the information for all space and the time points. So you probably cannot just say like your turbulence velocity is a Gaussian one. Then I probably cannot tell too much what exactly it is, but we do have the explanation at the previous section. but yeah, whatever. We just remember that the turbulence velocity fields are found not to be a Gaussian. The Gaussian field is fully categorized by the mean and the autocovariance. Yeah, so it's fully categorized. So in the random fields, that another concept that is very similar to the concept that we read in the random process. That is, in random process we got a statistical stationary, right? So that is from if we still stay at a certain point, and you move your time interval, you will get the same result. That is a statistical stationary, is relative to time, and we have the same concept in the space. Yeah. So it's like you have a x and a t. So if you're moving your time interval is like a t plus capital T or plus s as well, just depending on how you name your variables. And so at the space shifting, the position shifting, you can like x plus a capital X or plus another yes later. you can name your later, yeah. So in all points that you shift it a little bit. If you shift shift your position and you found out that the velocity field is still the same, then you can say this kind of field, the random field, is statistically homogeneous. So what was going to say that is a statistical. You probably can imagine that the statistical a homogeneous this homogeneous thing, statistically homogeneous. It can happen. Like they give you example like a wind tunnel. In the wind tunnel experiments, the homogeneous turbulent is the simplest class of flows to start using direct numerical simulation. That is what they say. But guess in the real world application, you probably still can find an example of the homogeneous turbulence. So I probably will skip this point, but you can just like easily to find that example. And another, I would say another different kind of concept is like isotropic. So for homogeneous and isotropic is probably is like a little bit different. So I will read the part of the sentences to let you know if how they say the isotropic turbulence. So that is like if the field is also statistically invariant under rotation and reflection of the coordinate system, then it is statistically isotropic. So if the homogeneous turbulence, you just like shift your position, right? So like if you get a rectangular, okay, a rectangular foot or a rectangular wind tunnel, okay, and it's very flat, even though it's a very flat, like the height and we have a length, width, and height, right? So the height is very small compared to your weight, and the length is goes to the infinity. Then you can consider that your turbulence from position x1 in the wind tunnel to the position x2 in the wind tunnel, that is all just following the direction of the lens, okay, following the direction of the lens, and you get this shift, you got the same velocity field, and then that you will call this homogeneous. But if you like rotate your coordinate, a little bit, like you probably will go like a 45 degrees off to the x1 direction or the lens direction, and you will find if I would say if you find that the velocity field is still remain the same. I would say the same is not exactly the same, is like statistically the same, then you can call that is isotropic. So the isotropic is like yeah, we got the same value. We got the same value in every direction, right? That is the definition of isotropic. So in the wind tunnel, we probably can also produce. I'm not very familiar to the wind tunnel experiment actually, but what is they say is that hundreds of the wind tunnel experiment has been performed on isotropic turbulence. Yeah. So that is one of the definition. So while we discussed about the homogeneous and isotropic, the thought in my mind like yeah we start with the things that is simple, right? You just build your knowledge from the simplest one and build up and up and layer up. Yeah. So I would say that it's probably just like a kind of simplification to your turbulence flow. We probably cannot directly go to the most complicated one. We probably cannot deal with that, even though with the state of art technique, some kind of the problem cannot be solved still. Okay, so the the lens the red scene of the random fields, it didn't get too much explanation, but it just like go to the 2-point correlation in the homogeneous place or not homogeneous is yeah, and it get the wave number spectra. So basically like you get a 2-point correlation. It's like you choose a distance, right? 1.8 point at x1, point at x2, and you take the correlation here. And so you will get a length scale here. And if you like transport, transform, sorry. Oh, and I was finding the term transform. You transform your length scale into the frequency domain, like using a Fourier transform, right? You use a wave number spectrum to do that. Yeah. So you probably no. This is a little bit complicated. Confusion here, but so I would say you choose two different points and you got the length, and you change your length to the wave number, and you once you get a wave number, like yeah. So you can get a spatial Fourier form, and you can do the Fourier transform. So that is exactly the same concept. It's just like based on a different variable, and this kind of variable is exchangeable by like a Fourier transform. We don't need yeah. So I don't think it gave me I would say that probably will be essentially enough, but it's not that enough to let you catch the all concept of this. So I will just stop here for the spectrum function. But yes, so the end of this chapter is like it goes to the turbulence kinetic energy and turbulence kinetic energies spectrum function. Yeah, but I think we will get back to this very important spectrum in the latest section, I think. Yeah. No hurry to solve this at this point. Yeah. So the 3.8 is called the probability and averaging. So I would say that the main concept is just let you know there's the probability is like you toss a coin, you assume that the true probability that you get the head and you get the tail is both equal to 0.5. Yeah, but if you actually to do the experiment, you will get a very close observed value of the probability, but you will never get the true probability. That is 0.5, which is you say you probably say that is a true one, if you can say that. Yeah, but this is the same concept here. Is like you will have a true mean velocity here. Okay, we probably let's just call it true for the convenience. Yeah, but you like you can, but it's a truth, right? But once you get numbers of the velocity, no matter what you are going to do, is the turbulence process or you got a field, or you got the numbers, a test for this, and you got an ensemble averaging or time averaging. You will probably not get, or spatial average. Yeah, you have different kind of averaging skill method to get the mean velocity, right? But those kind of averaging cannot actually get the definition of the mean. Okay, that is the concept of this section. Yeah. Averaging, not the mean. You will never get the mean for it. Yeah. Okay. Yes, is that it's probably too rough to say that you will never get a mean, but it's hard to get a mean. It's hard to get a mean. I got the point. I got the credit. Okay, so we have the last part that I read is mean flow, the mean flow equation. So the mean flow equations, that is the part I am familiar with. Familiar. Yeah, so we get into the Navier-Stokes equation here. Okay, so as we mentioned that for we got a turbulence in the description of a probability. We have a fluctuating velocity and the mean velocity, right? So we can also use this concept, the decomposition concept, into our true velocity here. So the Reynolds equation is start from here. So we separate the actual velocity, like whatever you mention, or you not mention, you measure. Sorry, I used the wrong word. You measure from experiment or whatever. So the actual velocity can be decomposed into fluctuation and mean. Okay, so it has a name here. It refers as the and sorry and if we put this decomposition velocity into the conservation of mass to the equation of the continuity equation for the incompressible flow, okay, for the steady and compressible. Do we need to be steady here? Okay, we don't need steady here, I think. But whatever, it's like yeah, probably need steady because it dropped the term, the partial t, partial u, partial t term here, so it should probably need a steady state. Let's see. Let's see the deviation of the continuum equation. That reminds me. So it can be unsteady because we are in compressible flow. So it's no worry about steady or not steady. Sorry, that is my fault. Yeah. So continuum equation that it comes out for the divergence of the mean velocity is equals to 0, and the fluctuation divergence of the fluctuation also goes to 0. And then we turn into the momentum equation here. We did the same thing, we do the same thing and we want to get the Reynolds decomposition for the velocity. Okay, so in the momentum equation, we have two velocity components that is getting together. So I need to remind that the first step here to get like you got the momentum equation here, and the first step is to write the substantial deviation into the conservation form. Yeah, it's very simple. You just like combine your conservation of mass of the equation of the conservation of the mass into the momentum equation, and then you can get the mean of the substantial deviation here. Then when you substitute in the Reynolds decomposition for the UI uj, I use a tensor notation to do that. Yeah. So the nonlinear term ui times uj can become the mean ui times mean uj plus fluctuation ui times uj and take the averaging. Yeah. So then now we can see that using the decomposition method, we can get a small ui, small uj, and this term is Reynolds stress. That is the differences from the original Navier-Stokes equation. Like we got it like this is called the Reynolds equation. Yeah. I think we have a Reynolds average. Rens, you probably have heard of Rens equation, but I think probably we will have Rens equation in the later. Is kind of different or not. I'm not very sure about that. Whatever. Fleeting. Oh, okay. So I think that is the main concept. So we got the Reynolds stress here from the decomposition method. Yeah, that's fair. Okay. So, so for the next time, if we got a new book, the Elegant Universe, we will get start from a new reading. Get start reading the new book. But if not, I will keep reading Turbulence Flow, this book, and we will start from 4.2 Reynolds stress at page 86. Yeah, and we'll see what kind of information we will get. Interesting, right? I'm just like talking to myself and I say interesting, but it's actually no one seeing this book with me. But yeah, reading is just like this kind of thing. Like you read your book and he reads his book, her read her book, she read her book, and the main concept is to read a book, right? We sit here and read a book. In this like we have a well-developed internet network here. Probably people don't read a book very often. Yeah, is a chance for everyone to sit down and read a book. Yeah, or even probably you can pick some. It is possible. Pick some books that you like and you can recommend to me. I recommend for me, and I will try to get that book and we can read the same book together. Yeah. 好，今天直播大概就到这里结束喽。OK，我们下次见，明天见。